Get started. It's 11:02 now. In the interest of time and ensuring that we finish whatever we plan to do today, let's get started. Thanks again for joining. This is our 11th series in the 3 AI webinar. And this morning, we are going to talk about essentials of deep learning. And today's webinar will give you a deep dive into concepts of deep learning with few application scenarios. Our speaker today is Sundar Ramalingam, and who is also our thought leader at 3AI. Sundar is heading deep learning practice at NVIDIA India, and by education, he's a mechanical engineer and has got masters in business administration. He has a strong technical background, and his areas of interest include deep learning, big data, IoT, and automotive solutions. With over 20 years of experience in solutions involving visual computing, virtualization, and high performance computing, he's also got exposure, high computing, right? It's a pleasure to have him with us today. In addition, he's also got exposure to work cultures across multiple countries in Asia-Pac region. AI in itself has evolved and improved methods of data analysis and complex computation. Solving problems that seemed well beyond our reach only a few years ago is now realistic. So today, deep learning is transforming every industry, from healthcare to retail to automation to automotive to financial services. In this webinar today, Sundar will actually do a deep dive into these concepts. And along with it, we'll have multiple scenarios followed by Q&A by all of you. I am sure his expertise will provide us a great exposure and learning, and it'll be worthwhile all of our time sitting here today on Sunday morning. Personally looking forward to hearing from him. Before we get started, some housekeeping rules. Please keep yourself on mute. We will allow you to ask questions and call out your name if there are specific questions that we want you to ask in person. Put all your questions in the chat window so that we can collate some of these questions that are similar and ask Sundar the questions at the end of the session. We will give about 15-20 minutes for Q&A. And all the questions will be taken in lieu of time constraint. If we are not able to answer any of the questions, we will take it towards the end. We will make sure you will get response over email. We don't see that scenario because we plan to cover most of the questions. With that said, without further ado, let's get started. Over to you, Sundar. Thanks again for joining us. Pleasure having you in this webinar.
Thank you, Sarah. Thank you for the nice introduction, and good morning, everyone. It's a real pleasure to see a lot of people showing interest and dialing in on a Sunday morning to learn about the new concepts, which is taking the world by a storm. So, as we all know, the theme for today's webinar is Essentials of Deep Learning. And we are going to cover the very fundamental concepts. And we specifically have designed it in that fashion, primarily because there are many terms that are used, or I would say misused in the industry today, pertaining to AI, deep learning, machine learning, etc. A lot of people with whom I have interacted think that it is a very esoteric topic and only intellectuals can understand what it is and apply that in their actual work, which actually is not true. It is, I would say, a continuation of the way technology has been evolving over the past several decades. And what we are seeing today is nothing new. Only thing is, there are a few changes that happened in the recent past. When I say recent past, what I mean is about 7 to 8 years' time, which has revolutionized the way AI has been working. And that is what we are going to learn this morning. My talk should take about 40 minutes. That is how I have designed it. And at the end of 40 minutes, I hope you will be able to go back with a lot of confidence of having understood a lot of terminologies that are being used in the world of AI today. So we know that there is a lot of disruption that has happened in the way information is used in the recent past. data has been used in the recent past. The well accepted and well proven technology is the heuristic way of working things, which is nothing but the computerized programming concept, which we are all very comfortable with. So basically, how it works is that if this is the condition, this is the result, else this is the result. That is how it works, and we are all very comfortable with it because the output is 100% dependable. We know exactly why that output has come that way. So it's fantastic. We all like it. We all believe it. We all trust it. Then comes machine learning. So in machine learning, the very basic fundamental need for machine learning is that it can make use of only structured data. So what I mean by structured data is something which can be read by a machine. The simplest form of structured data that I can cite is Excel data. We all are very familiar with Excel, and any Excel sheet can be read by a machine, and you can derive a lot of intelligence from that machine. Obviously, this is just not Excel data. There are many other complicated data that also be either classified as structured data, or even if it is in an unstructured format, there are ways and methods of converting that into structured data. Now, so machine learning needs structured data, point number one. And point number two is that if you take any domain, let's take healthcare, retail, Internet of Things, whatever you are comfortable with or in which you are working, in any domain, the amount of data that can be classified as structured would be somewhere around 20% of the full data that is available in the domain. What I mean by that is, if let us say if the total data that is available in the domain can be taken, about 15-20% of the data would fall under the category of structure, and the rest will fall under the category of unstructured. So unstructured data obviously cannot be dealt with that easily with machine learning. There are many hurdles to be overcome to do that, and hence machine learning, the accuracies of the predictions that you get from machine learning techniques, most of them always remains at around the mid-70s. About 75-76% accuracy is what in general can be expected from a traditional machine learning technique. And then comes deep learning. Actually, deep learning has been done for many decades. You'll be surprised to hear about it. But it never had a real start. There are many false starts and a lot of R&D went into it, but then it never had a real full start until very recently, primarily because data was not available in a big way. And deep learning, one big difference between machine learning and deep learning is that deep learning can make use of unstructured data also. So because deep learning can make use of unstructured data in addition to the structured data, almost the entire corpus of data that is available for a particular domain can be made use of for making your decisions. Hence, deep learning took the accuracy levels far ahead. And today, for many problems, not for all problems, for many problems, accuracy levels in the range of mid-90s in terms of percentage, or sometimes even the high 90s percentage is becoming common. Hence, deep learning changed the way AI has been working, machine learning has been working, and today we are having this seminar. So many people are showing interest in this. It is because of the change, the big change that deep learning brought into the world of AI computing. Right. So one footnote here is that it actually is wrong to say what is the difference between machine learning and deep learning, because machine learning you can imagine machine learning to a broad set, and deep learning is a smaller subset inside machine learning. So if machine learning is a bigger circle, deep learning is a smaller circle contained inside the bigger circle called machine learning. But throughout my talk, when I say machine learning, what I mean is the traditional machine learning techniques, and deep learning is deep learning, as you know. Right? So interestingly, as we had discussed, deep learning brought a big change in the way AI has been working, and a lot of companies started showing interest in adopting it. Still, it is not fully adopted. But I have, in my capacity as the work that I'm doing in NVIDIA, I'm interacting almost on a daily basis with all technology heads, so CTOs, CIOs, CDOs, etc. And irrespective of whichever domain they are in, they are feeling a pressure to make use of the modern techniques. They feel sort of left behind if they are not using the modern techniques, and they feel a little bit threatened when they hear their peers in other companies to start talking about newer techniques being adopted. And one of the popular surveys, as you can see, showed that 84% of the execs feared missing their growth objectives and missing out to competition if they don't scale on AI. And of that 84%, 76% of them, which is a huge percentage, struggled with the notion of, hey, how do I get started? Where do I start? I mean, this seems to be changing every day. Where do I get started? And how do I adopt it and scale it all across the enterprise? That is what 76% of the people were worried about. And I will try, within the limited period of time, I'll try to dispel that fear as much as possible this morning. Now, let's understand the fundamentals of machine learning and deep learning. Let's understand what exactly it means. I'm not going to get into any mathematical equations and weight modifications and hyperparameter tuning. We will all reserve that for maybe a second session sometime later, a few months later. But purely from an approach perspective, for a person who need not even not even interested in getting into the mathematics of it, how do I differentiate between a machine learning and a deep learning approach? It is this. Machine learning, as we know, uses structured data. And for understanding the structured data, you need to understand the features or the commonalities that are hidden inside the data. This is called feature engineering. Understanding the features, extracting the features from inside data is called feature engineering. In machine learning, feature engineering is done through handcrafting techniques. What I mean by that is a domain expert who understands which domain they are working in, if it is medical or retail or Internet of Things or cloud or whatever it is, a domain expert who understands the data handcrafts the features that are hidden inside the data. And he has to write handcrafted algorithms that are able to describe the data. Hence, machine learning is highly, the feature engineering is very human dependent. The feature extraction is done through human beings who handcraft this data, handcraft the features. That is what is the fundamental approach of machine learning without getting into the mathematics part of it. I'm not going to talk about linear regression and things like that, not right now. So how does deep learning work? How does deep learning work differently? In deep learning, the feature engineering is not done through handcrafting techniques. And what it does is, so you write algorithms that enable the machine to look at huge amounts of data, very large amounts of data, and understand the commonalities and the patterns that are hidden inside the data. I repeat, your algorithms, your deep learning algorithms enable the machine to look at large amounts of data. When I say large, it's like humongous amounts of data, and understand the patterns and the commonalities that are hidden inside the data. Now, if you take a step back, if you have understood the patterns that are hidden inside data, if your algorithms can learn from the data, if they can get trained from the data, it is nothing but the features that belong to the data. I hope you are able to correlate this. Earlier, what we did in machine learning, we handcrafted those features. A domain expert handcrafted the features. Whereas in deep learning, the algorithms sieve out or pick out, extract the patterns hidden inside the data, and hence they understand, they get trained on the features of the data, and they learn the features of the data. Hence, feature extraction or feature engineering is done through algorithms, and the algorithms learn the features. And that is the big fundamental difference between machine learning and deep learning. Now, so deep learning, as I said earlier, the big difference between deep learning is since you don't have to handcraft the features, you are able to use at least about 80 to 85% of the data, which falls under the category of unstructured data in any domain, and hence the amount of data that is taken into consideration for making your decisions, for predicting the behavior of models is all much, much better when compared to a machine learning technique. And hence, the accuracy levels went all the way up to mid-90s to high 90s for several of the deep learning models, if not for all of the deep learning models. So that is the reason deep learning has changed the way AI and machine learning has been working for the past several decades. So I hope I was able to explain that clearly. If you have any questions, please do type it in the chat window, and I'll try to answer them at the end of the session. So the next question is, what are the broad classification of problems in a deep learning approach? Okay, whatever you're seeing on the screen, there are only 5 classifications. I'm trying to make it as simple as possible, just to drive home the point that once you have understood the fundamentals and the approach, it is quite easy to get on to the bandwagon and have a smooth sail. Right. The topmost one is deduction. Whether to find something is there or not, yes or no. Right? Healthcare could be deduction of a particular disease, or retail could be advertisements, targeted advertisements, etc., etc. Then comes classifications. Once you have detected something, how do I classify it? A classification can either be a binary classification, which says it's either this or that, or it could be a multi-class classification, where you are, for example, you could classify it as a dog or a cat or a horse or a human being, etc., etc. That is the example of a multi-class classification. Then comes segmentation. If you have to pull out one particular area or volume from let's say images, that's what is meant by segmentation. And then based on the deduction, classification, segmentation, if you have to predict an outcome, an intelligent prediction from what is it for these type of events that are likely to be triggered, for these type of conditions to exist in a scenario, what is going to be my prediction is what is a prediction of what is likely to be an outcome. An example could be, say for example, if these are the conditions that are prevailing in the market, what do I predict the stock price movement is going to be? That's an example for a prediction. And there will be several other ways of prediction. A prediction of when exactly this aircraft turbine is going to fail, and hence do predictive maintenance and not a scheduled maintenance. That's another example of prediction. And then, of course, comes recommendations. Once you have predicted something, obviously you'll be able to make very intelligent recommendations to the user. The easiest would be, the ones that are used in e-commerce industries. What is the recommendation that I should give to this type of a user so that he has a high likelihood of buying my commodity rather than leaving it in the shopping cart and not buying eventually? So that could be an example of recommendation. So any deep learning problem can be classified under these 5 top heads. You either direct or classify or segment or predict or recommend. That is what you do through deep learning. Now, deep learning has got two broad work streams, I would say. The first work stream is what we call as training work stream. I'll explain this with the help of an example. Let's take the classical use case, a textbook use case, which is face deduction. The area of creating neural networks. Neural networks are the backbone of deep learning. The algorithms that enable, or the models that we create, they are based on a principle which is called as neural networks. And the act of defining the neural network and enabling the neural network and training the neural network to detect faces. If I am walking into a railway station or I am walking into an airport gate, the ability of the camera to detect my face as belonging to this person, that is what is face deduction. And the training happens always in the data center. And the data center will have huge amounts of data which will enable you to train, and it will have enormous computational power, huge computational power, because training needs humongous computational power. That is what is training. And the second work stream of deep learning is inferencing. After you've created great training models and your test results show that they give you 95% accuracy, 96% accuracy, so you are ready to deploy it. The deployment is called inferencing. People use the term inferencing, deployment, or some people even call it as production. And so once again, if you go back to our previous example, face deduction, you have created great neural networks that can detect faces and that resides in the data center. There is no use. it has to be deployed at the airport gate. It has to be deployed at railway stations. It has to be deployed at police chowks, etc., etc., where it does the work of detecting faces, where it is put to use, and that is the inferencing part of it. Now, both these are two different ways of working, and the computation needs, the way they are deployed, the software that supports both these things are totally different. What works well for training is very different for what works well for inferencing in terms of technology and in terms of economics of usage. So that is what is the difference between training and inferencing. So as a quick recap, in the first section, what we discussed is, we discussed how data analytics has evolved in the recent past, heuristic techniques, machine learning, deep learning. We understood the difference between machine learning and deep learning. Machine learning, you do handcrafting of features. Feature engineering is done through manual techniques, whereas in deep learning, you write algorithms, neural networks that enable the machine to look at data and learn from data to pick out the commonalities and patterns hidden inside the data. And then we talked about the two work streams of deep learning, which is training that happens in the data center and inferencing, which happens on site where it is put to use. That completes chapter 1 of my talk. Chapter 2. A lot of people used to ask me, nowadays that is not the case because I think too many people are aware, but people used to ask me, hey, what is NVIDIA doing in this area? Isn't NVIDIA a graphics company? Yes, we are a graphics company. But NVIDIA is playing a very central, pivotal role in the area of AI computing, deep learning, machine learning today. And the reason for that is this. As I mentioned earlier, data was not available, hence deep learning never took off in the real sense. But data became available from two different sources. The first one is the Internet of Things, where anything and everything got fitted with sensors. And the second stream, which provided a lot of data, is social media. So thanks to Internet of Things, sensors, and social media, the gap of not having data was fulfilled. The second reason for deep learning to never have a practical approach until recently, until 6-7 years ago, is because deep learning as a technology needs enormous amounts of computation. You cannot do deep learning problems, practical deep learning problems, and use it for inferencing for production with the traditional ways of computing. And the reason is this. As we all know, the traditional ways of computing works with the help of CPUs. And the CPUs are basically serial computing engines. Whereas GPUs, the fundamental approach of GPUs is that GPUs are parallel computing engines. What do I mean by parallel computing engine? So in a parallel computing way of working, what you do is you take a large problem and you break down the large problem into a very large number of small threads. Okay, I repeat. You break down the large problem into a large number of small threads. And each of these threads is run in parallel. I always explain this with the help of one example, one very simple example, which drives home the point very well. Let's assume that you need to drive down from Bangalore to Mysore, and what you have today is a 6-lane highway. But in order to increase the throughput, in order to make like 100,000 or 1 million cars to move from Bangalore to Mysore very fast, what do? Instead of using a 6-lane highway, you build a 10,000-lane highway, right? So the point A is fixed, point B is fixed, the number of cars is fixed, which is 1 million, but you are able to transport that 1 million number of cars much faster by constructing 10,000 lanes of highway instead of the current 6-lane highway. And that is the fundamental of parallelization. And the fundamental GPU architecture is a parallelized architecture from hardware perspective and from software perspective. And hence, for running massive computational problems, if they are amenable for parallelization, this is very important. Not all problems can be parallelized. Then you cannot construct 10,000 lane highway everywhere. Only a few problems, a niche set of problems can be run in a parallel fashion, can be run in a parallelized fashion. And as needless to mention, the deep learning, machine learning, many aspects of AI computing can be run in a most efficient parallel fashion. And hence, for running deep learning problems, computationally very intensive problems which are amenable for parallelization, like deep learning, GPUs are the most preferred way of computation. And that is where GPUs and NVIDIA play a big role, because GPUs are fundamentally parallel in nature. The architecture is parallel in nature as against a CPU, which is a serial in nature. Now, GPU, I'm not deselling CPUs. That's not the idea. CPUs and GPUs coexist, in fact. And for a large set of problems which run in a serial way only, CPUs will continue to be the preferred mode of computation. Whereas there are high-performance computing problems, parallelized problems, where a CPU cannot really help, and that is where GPUs come into play. All right. So let's now very quickly move on to the use cases of deep learning. Having understood what is deep learning and why NVIDIA plays a big role in that area, we need to ask ourselves, so where is deep learning used? And it is very safe if I answer deep learning is used everywhere without exaggeration. It could be the internet and cloud. The recommendations, if you go to any e-commerce website, either an Indian website or one of the international websites, and try to buy something, a lot of AI and deep learning goes into the recommendations that are served to you, the content that is served to you, in ensuring that the right content is served to you and not a wrong content that is served to you. If you are going to search for a full sleeve shirt, a men's shirt, a half sleeve shirt or a woman's shirt should not be served to you, and that is all happening through a lot of AI, deep learning, machine learning techniques. And the second very important one is medicine biology. We'll talk about it in detail a bit later. And then comes media and entertainment. As we all know, there's a deluge of data. There's so much images and video and content that goes into the internet every day. Those statistics are like mind-boggling. Now, how does a company like Facebook or one of its peers, how do they ensure that objectionable content doesn't get uploaded? Because some Tom, Dick, and Harry uploads an objectionable content onto the internet. The company that holds the content may run into problems. So, understanding the content, removing unwanted content, unacceptable content, explicit language, explicit content, etc., violence, etc., all that is now done through deep learning techniques. So, machines help human beings augment the effort of human beings in understanding content and doing the right thing on the content. Then comes security and defense. Like there are tens of thousands of cameras that are fitted in every city today, in every town today, and in a country will have millions of cameras, and the globe will have billions of multi-billions of cameras. Now, how can I make sense of so much of video that gets streamed out of these many number of cameras? How do I pick out, let's say, a suspicious activity, or a car jumping a signal, or somebody not wearing a seat belt inside the car? How do I pick out that particular incident of interest to me? That is all done through deep learning today. All the modern safe cities, smart city concepts, they are all built on deep learning today. Last but not the least, autonomous machines. The epitome of deep learning, I always believe, is autonomous machines. We hear so many things about self-driving cars and things like that, right? And when you get onto your car and when you drive home from your office, your brain does so many complex things which you don't realize. But teaching a machine to do those complex things that are done by a machine is no small feat. And hence, autonomous machines is the epitome of deep learning. And it's an extraordinarily complex science, extremely complex technology that is changing the world is working. And that is surely going to change the way we are going to commute in the near future. And that is all done through deep learning. Now, this I would say is a summary slide. I'm going to get a little deeper into a few of the domains. I'm not going to pick up every domain that I talked about, a few of the very interesting domains. The first one is real-time streaming video analytics. As I said, streaming video is coming from millions of devices, millions of cameras. Some are smart, some are not smart cameras. How do I make sense of that? It could be for access control, it could be for parking management, traffic engineering that we discussed earlier, optical inspection in a manufacturing line where the conveyor belt moves very fast. How do I pick out one component that did not get assembled properly, that did not get welded properly? Optical inspection, logistics, content filtering, we talked about this. So all these deal with streaming video. I'm not talking about static images, streaming video. That's a place where deep learning is going to help us, is helping us in a big area. Now, if I drill down a little bit, things like vehicle detection, number plate reading, somebody not wearing a seatbelt, somebody speaking over the phone, and face detection, face alignment, crowd density analysis, etc., etc. All these things are done through deep learning today, and they are very, very elegant, very advanced techniques that give you very high levels of accuracy, right? And then comes the things, the Internet of Things. Now, as I mentioned earlier, anything in the world gets fitted with sensors today, from aircraft turbines to rockets in the sky to the cows that give us milk. Everything is fitted with sensors, and they measure and they give signals about a multitude of things. How do we make sense of so much of sensor data that is done through deep learning today? And I'll just pick out a couple of examples. The first one is a concept called as digital twins, which is a very commonly used. Digital twins are used in aircraft turbines today. So, what is a digital twin? For every aircraft turbine that flies in the sky, there is a digital representation of that turbine in the lab. See, I'm not talking about every model that flies. Say, for example, let's say A380 uses one model of turbine. I'm not talking about one A380's model of turbine has a digital twin. No, that's not what I'm doing. Every serial number of the engine. Let's say A380, there are only 100 aircraft. That means there are 400 engines in the sky. And serial number 1 has a digital twin. Serial number 2 has a digital twin. Serial number 400 has a digital twin. So every individual piece of turbine that flies in the sky, A380 is just an example. I mean, I don't know A380 digitally has a digital twin. I assume it will have. But what I'm trying to say here is aircraft turbines are using digital twins a lot today. And these digital twins simulate the temperature patterns, the stress patterns that are observed in each of these twins. And hence, you will be able to predict the failure of each of the individual engines. The reason to do that is, today, maintenance is done in a scheduled way. What I mean by that is, this model of the turbine has to be maintained once in 6 months, once in 9 months. But not all the turbines fly under the same scenario, right? The altitudes might vary, the flying temperatures might vary, the grounding time might be vary, though they belong to the same type of aircraft. So it is a lot of money that goes because we want to do a scheduled maintenance. As against, if you are able to predict failure, you are able to predict that, hey, number 1 may fail in 6 months' time, whereas number 2 is not going to fail for 12 months. So number 1 has to undergo a predictive maintenance schedule of only once in 6 months, whereas number 12 needs to be maintained once in 12 months only, though they belong to the same model. That is going to save billions of dollars, because aircraft maintenance is not an easy thing. So, and not only that, inspection of railway trains, energy in the energy industry, large windmill farms, power plant equipment, unmanned probes in coal mines, underwater drones, etc., etc. A lot of places, IoT uses deep learning. And this is sort of a repetition of the previous slide. And there are many, many areas like, oil and gas, agriculture, optical inspection, railway platforms, railway lines, huge power plants, process plants, etc., where industrial AI applications are widely used today using sensor data. And then comes robotics, which I would say is an extension of this. Robotics uses a lot of AI, a lot of deep learning today, and it spans across almost all the segments that we described earlier. It is automation of manual processes, and it was happening earlier through other techniques. Now it is all deep learning based things where the environment is learned, and hence the robot reacts accordingly, as against a programmed robot which is programmed to do only what it can do, or it has been programmed to do. Here, robots understand environment, and hence they decide on site, in situ, at the edge. They decide how they are expected to behave, and hence behave accordingly. That's the big difference between an AI-boosted robot and a traditional robot, which we all are familiar about. And switching gears, another important area of deep learning is conversational AI. Mark my words, conversational AI is the big thing, the next big thing today. And it's going to change the way everything is going to work. Where you are able to talk to machines instead of typing to a machine on internet, instead of conveying your signals to the machine through some other fashion, you talk to a machine. And that's going to have a big impact on healthcare, robotics, finance, retail, etc., etc. Of course, autonomous machines also, where human voice is understood and reacted. And not only that, when you have to get interact with somebody and get a response, you won't even realize whether the response is coming from a machine or from a human being. And this needs enormous amounts of learning because this is highly contextual. This is just not understanding the syntax and the semantics of the language. Say, for example, if I say understanding a pronoun he, when I say he is very contextual. It depends on the previous usage where I refer to somebody else, and he has to be associated to that. Understanding pronouns is very, very contextual. If I say, do I need an umbrella? It is very contextual. When I ask my wife, do I need an umbrella? She understands that I am asking whether it is going to rain that day, that evening, while we are just about to leave the home maybe for a dinner. How do I make a machine understand that? The contextualization of human interaction is a very, very, very complex thing. And that is what conversational AI is achieving today. Right? And medicine and biology, another big area, particularly given the current unfortunate scenario that we are all witnessing all over the globe. It is assuming extraordinary significance. Detecting anomalies in medical images. Medical image could be MRI, CT scan, or X-rays, or whatever type of images, or understanding the drug discovery process, predicting the way a drug is expected to react to a protein structure, etc., gene mutation, etc. All these are now getting solved through deep learning and machine learning. So deep learning helps radiologists to make better decisions. It augments the effort of a radiologist and of geneticists in making good decisions. Another important area is the financial services, right? So it could be insurance or consumer banking or investment or corporate banking. Many areas where deep learning and AI techniques are getting used today. I'm not going to really read through the list. I'm sure you all can look at the list and understand. So you will realize that many of these areas are now addressed through manual techniques. I mean, things like credit risk analytics of a person or of an institution, or understanding the buying behavior or credit card swipe behavior of a person, understanding anomalies in the spending behavior, predicting customer churnout. I mean, predicting that, hey, this guy is going to move from my bank to another bank or from my telecom provider to another telecom provider. Risk analytics, I mentioned this earlier, portfolio optimization, trading decisions. There are many areas in which traditional machine learning techniques, which are widely used today, are slowly getting replaced by deep learning techniques. Now, we are moving to the last chapter of my talk today. Now, so we have understood, as a quick recap, we talked about the difference between machine learning and deep learning, why machine learning is hot today, the approaches of machine learning, training, and inferencing, and then we switched gears and we talked about the various areas and segments and applications of deep learning. Now, so everything is fine. So what happens in the background? What happens in the data center? As I mentioned earlier, neural networks are the fundamentals of building blocks of deep learning, and these are highly sophisticated, very elegant algorithms that are written by data scientists, and they predict once the input is given, they predict the outcome. That is what they do. And the complexity of the neural network is exploding. This is a pictorial representation of how it has exploded in the recent past, in the last 3 years. A very pictorial representation of how it has grown in terms of the complexity, in terms of the depth, in terms of the number of layers of neural networks. And it is just not the complexity. It also is the types of neural networks that is changing in a huge fashion. The first two columns, many of you might understand convolutional neural networks, or CNNs, which are used for fundamentally mainly for image-based analytics, and the neural networks which are used for time series data, speech, etc. These are conventional ones, traditional ones. There are several new ones which are getting born every day. Generative adversarial networks, which has really helped to bring up the accuracy levels, called GANs. And then there's a very niche area of learning called as reinforcement learning. And the last column, you will see that there are several new species of roles are being born. Like there could be collaborative filterings and sparse LSTMs and things like that. I don't have time to go into any of them. But as we learned earlier, it is just not the complexity of the network. It also is the types of network that are newer and newer networks are being born, primarily because of the huge research and development that is happening in this area. There is so much of interest in AI, and a lot of research goes into it. And newer methods and better methodologies, more precise, more accurate methodologies are evolving. All this means that you need enormous amounts of data and enormous amounts of computation, right? And that is what AI, NVIDIA plays a big role here, and there are purpose-built AI supercomputers that are helping to achieve that dream. And people who are following NVIDIA might have learned that a couple of days ago we made a very significant announcement called as the Ampere architecture, which is a new architecture that we have released, which has changed the way the way parallel computing has been working for the past several years. It is just not a frog leap in technology. It is a fundamental change in the paradigm of high performance computing, of parallel computing, right? And these are AI supercomputing systems. The DGX, the systems like the DGX A100, they are AI supercomputing systems that transform the data center. The data centers are now called AI data centers. And typically, AI data centers do not handle one or two of the models that we described earlier. They work on ensemble of models. Like what I mean by that is, yes, several types of models, several varieties of models, neural networks interact with one another and work in unison to help you to make good decisions, more accurate decisions. That is on the hardware part of the computation. The software part also is a very sophisticated software layer. And this slide shows you how the software stacks up in an AI data center. At the bottom of everything is the GPU-enabled parallel computing architecture, the hardware. On top of it lies a software library which is called as CUDA, which is the software parallel computing library for creating your software parallelization framework. CUDA is the fundamental building block. On top of that, there are several buckets of sophisticated SDKs and libraries. There are libraries for machine learning, for deep learning, high performance computing, virtualization, etc. And on top of that lies that blue layer, which is a very favorite layer of all of us, the frameworks. I mean, the frameworks like TensorFlow, Python, PyTorch, MX, Net, Microsoft CRTK, etc. These are very popular frameworks, and a lot of work goes into it. And on top of that lies the application layer in which you will be working upon. Now, the good thing here is that there are two good things
sorry
here.
to interrupt. Sundar, sorry to interrupt. Would you be able to wind up in next couple of minutes, because there are questions that are coming? Yeah. Thank you so much.
Saraswati. Exactly 2 more minutes, and thank you for the time reminder. Yes, thank you. Now, so you will be working upon the top layer, which is the application layer, and the two good things about this is that, number one, almost all the software is free. You don't have to buy anything. It is available free of cost. And number two, great companies work on this like NVIDIA, like Google, etc., and they provide them to you, which gives you the fundamentals, the fundamental building blocks free of cost. Now, thanks to all these developments, what is happening is that the cost of computation has gone down drastically. Okay? So the data center, which used to look like this earlier, thanks to all the new technologies that are born, is now looking like this. Okay? So before, it used to look like this. And now, by using the parallel computing techniques in terms of hardware and software, it is looking like this. So that is a big paradigm shift that has happened in terms of AI and deep learning and machine learning. And so what are the next steps? I leave the slide open and I don't have to read through it. There are many. This is just a partial list. Of course, there's only the NVIDIA resources are listed here. There are many such resources available where you can get started. And I would certainly encourage all of you to join the developer program. Number 3, developer.nvidia.com join. This is going to give you a lot of information, and you just have to have an email ID to join this forum, and that will really help you in ensuring that you are up to date in terms of the technological developments that are happening in this amazing world. Okay, thank you again for this opportunity, and I now give it back to Sarah for the Q&A session.
Thank you so much, Sundar. Very lot of learning, lot of domain details as well. Thanks for the wonderful session. There are quite a few questions. We'll see how much we can cover. To start with, going back to your first chapter about data structure, question is around why do we have so many challenges with structured and semi-structured data compared to the unstructured data?
No, it is not the challenges of handling structured data. That is not the idea. See, structured data can be handled very well through machine learning. There is no doubt about it. Machine learning can handle structured data beautifully. No problems there. But the challenge is because for a particular domain, only about 20-25% of the data maximum will be structured data. So what of the data that is available, you are able to use only a small chunk of the data when you are employing machine learning techniques. It is not that you are not able to handle the data well. You are handling the data well, but it so happens that the data pertains to a small fraction of the whole data that is available for the particular domain. Using deep learning, in addition to structured data, you are also able to use unstructured data, and hence the entire gamut of data pertaining to that domain can be made use of, and hence the accuracy levels are better. It is not that structured data cannot be handled well. That is not the idea.
Thank you, Sundar. We have our next question by Siddharth, and he's asking, based on his experience, it becomes difficult to explain to stakeholders the results of deep learning algorithm. While there are defined architectures, the internal calculations are very complex and explainability of these results become a challenge. Any thoughts around that?
So Siddharth, explainability of models, prediction of a result is an ongoing research field. We have made a lot of advancement in it, but we are not there yet. Can a model's behavior be completely explained? The answer is no today, right? So, but there are many tools that are available which help you to reach that stage, but we are not there yet, and that is a big area of research that is happening in deep learning today. And the reason for that is, if I get into the neural networks, the ability to extract the middle layers, understand and predict how the middle layers work is a bit abstract, quite abstract today. And that is the reason for that limitation that we are having today.
Thank you, Sundar. Our next question is by Prashant. How easy or difficult is it to learn AI ML from the basis of somebody who has got non-engineering background with zero coding, but want to grow in the industry of ML and applying these principles to his core area? For example, it could be pharma or it could be medicine. How difficult or easy is it?
So first of all, congratulations, Prashant. I really want to applaud your eagerness to get into this field in spite of not being an engineer or having an experience in coding. So certainly, experience in coding and understanding the basics of mathematics, I would say, really helps. Is it an absolute necessity? It's a bit difficult to answer that question, but I can very comfortably say that a background in coding, understanding some level of having some experience in coding will really help to get into it. So I would encourage you to start with some level of learning a little bit of coding at least before you venture into this, because not having any coding background and not being an engineer, which means you don't have a mathematical background, it may not be that easy to get into it. Having said that, You don't have to be born as a data scientist to get into this field. So long as you have been working in coding field, you know some sort of C, C++, particularly Python, etc., etc. You certainly can have a decent beginning in the new area, and it all depends on your your personality as to how quickly you pick up and progress in that area.
Thanks, Sundar. That's encouraging. We have next question from Ankur, and his question is, what different roles need to come together to create, train, and deploy a deep learning enabled platform? Say, for example, a traffic management or challenge generation platform. What are the different things that need to come together?
Well, you need data. You need data. No data, no deep learning, period. You need enormous amounts of data, right? That is number one. And you need huge computational power. Deep learning needs computational power. It needs parallel computing approach. If you try to stick to the conventional, traditional ways of computing using CPUs, it's not going to work. It's not going to work in the sense that a small problem will take like 10 hours to solve. I mean, nobody will have practically it doesn't work. I mean, you need to get results faster and quicker and more accurate. So data is certainly needed. 100% good computational power is needed. Parallel computational power is needed. And the good thing about deep learning is not everybody needs to be a domain expert. I mean, don't get me wrong. I'm not telling that deep learning does not need domain expertise. 100% domain expertise needed. But an architect and the people who manage the projects and people who design the solutions obviously have to understand the domain. Whereas the person, the entry-level developer, entry-level data scientists who only need to either engineer the data or work on the data and create models, he need not be a domain expert in a healthcare or or a retail segment. They can handle data as data. So that way, the good thing about so you need good, skilled people who understand domain at the higher level, management level, who architect the solutions, and you need data and you need computational power. I would say these are the ones that are needed. Okay.
Thanks, Sundar. The next question is, close to home. So the question is, even with current advancement in CPU technology, how important is GPU acceleration for deep learning?
Right. So certainly, my idea is certainly not to make it as a marketing talk. I can do that very well, but that's not what I'm here for. For this session, no, I'm not here to market NVIDIA. So as I in this session, as I said earlier, deep learning AI computing needs enormous computational power, and that enormous computational power can only be achieved through accelerated computing techniques. Accelerated computing techniques work on the fundamental principle of parallelization. By parallelization, what I mean by that is you take a large problem, break it down into a large number of small threads, and instead of running these threads one after the other, you run them in parallel. Think of the example that I told you, 6 lanes and 10,000 lanes. And the massive computational power needed for deep learning, for machine learning, and the huge amounts of data that it needs to handle necessitates that you run it on the parallel computing fashion, not in a serial computing fashion. If you run it in a serial computing fashion for understanding, for playing around, for learning, it is fine. But if you want to really deploy something, pick up a problem, really run it and deploy it, running it on a serial computing architecture will practically be limiting to you, because you cannot wait for hours and days for a problem to get solved and then apply a different set of hyperparameters and then run it for more number of epochs, increase the batch size, all those things, experiment with multiple levels of network, different types of networks. Those type of permutations and combinations and hyperparameter tuning and batch sizes tuning, playing around with it is not practically possible if you have to wait for hours for one solution to converge. There you need GPU computation because it provides you parallel computation, which is an accelerated way of computation.
Thanks again, Sundar. There's one question which relates to a specific learning thing and specific geography. Please feel free to say that I mean, it's okay, we can get back to this if there is specific, right? But the question is, which university is having great courses related to AI and data science in context to implementation of all of these tools in healthcare industry, mainly in Canada?
I honestly don't know an answer to that, but I know that the University of Toronto is like has a very far advanced AI techniques that are used. I mean, many of the forefathers of deep learning were born out of that university. Whether they do, I'm sure they would be doing. But on your particular question, whether they do a lot of what type of healthcare work they do, I don't know. But I'm very confident that they'll be doing. Another one is Stanford. Of course, that's not in Canada. Stanford, in collaboration with Johns Hopkins University, Johns Hopkins Hospital, they are also doing extraordinarily advanced work in the area of healthcare and deep learning.
Perfect. That was precise answer. Thanks, Sundar. There's one more which says,
Sure.
what is the logical learning ladder for becoming a data for learning deep learning?
Okay, so I would rephrase that question as what is the logical learning ladder for being a data scientist, right? Because deep learning is a broad umbrella. I don't know how experienced you are, the person who is asking this question, whether you want to be an architect or you want to be a developer, a data scientist, data engineer, etc. So if you're a data engineer, data scientist, and if you have some programming background, you can get started on in this area. You need to learn frameworks, and you need to understand Python very well. I mean, that really helps for languages like Python or etc. If you have an exposure, that really helps you and accelerates your learning curve, and you can start using it. And anybody above that, obviously, we need to have a clear definition of the job profile in order for me to answer that question. But if you're a developer, as I said, some good programming background and the ability to think from a programmatic, object-oriented approach is what is needed. And I always have felt that learning a programming language, is not a big deal at all.
With you on it. Sundar, Divesh has a question. It's a long one, so I'll ask him to speak up for himself. Divesh?
Thanks, Sarah.
Yeah.
Thanks, Sarah. I hope I'm audible. So, first of all, thank you so much, Sundar. My question is, pretty much related to the one that you just answered. Now, when we talk about some domain-intensive functions, and I'm talking about, let's say, healthcare in this case, wherein we have a dichotomy or a dichotomous situation right now. We have scientists, who are very good with their understanding on the science behind the drug development, the drug discovery. Then we have data scientists, as you said, data scientist who is at an entry level, maybe 2, 3, 4, 5 years of experience, may not necessarily need the domain expertise. And he or she is in the process of building that domain expertise. Now, in the meanwhile, for the business problems that are existing at the top layer, how do they get translated to the data scientists? Because the scientists or the business people, they don't understand the concepts of data sciences, deep learning, machine learning that well. Folks who are practicing deep learning, machine learning, data sciences, they may not understand the business problems that well. So how do we stitch these two layers of the industry? So I hope that makes sense as a question, Sundar.
Sure. Certainly. Divish, sir, good question. Thanks for asking that. I mean, once again, I would encourage you not to look at deep learning, machine learning from a different lens like what you have been looking at IT as a field today. I mean, let's forget deep learning, machine learning. Let's look at the conventional, traditional computing approach today, programming approach today. I'm sure the architects and the project managers and the senior management, they cannot. I don't think they can program that well in C or C++ language, right? I'm not talking about deep learning at all, okay, machine learning at all. The traditional heuristic way of working today. But how does that enterprise work? But it has been working beautifully for the past 20, 25 years, extraordinarily well, right? So the ability to translate a business problem into a programmable problem, it's like writing the screenplay for a movie. I mean, once you have the the story, how do you write a screenplay? That's what one has to do. And that is why there are several layers of executives who work in an organization, from the basic developer to project managers and project leads and architects and business leaders, etc. And the ability, whatever has been happening earlier in a traditional computing area, that needs to be extended to the newer methodology also. That is why I want to repeatedly tell you that please do not imagine or visualize that this is a very difficult and esoteric thing that is difficult to learn, difficult to adopt. No, it is different. And change management and the ability to change from the current way of working to the newer way of working is what is needed. Of course, it is more complicated, technologically more advanced. I don't want to oversimplify also, but that is not something which cannot be done or it is too difficult to be done. Once you have the right set of leaders who understand technology, who can translate that into something which can practically be handled by data scientists and data engineers with the help of an architecting layer in between, the problem can be solved. So to answer in a nutshell, it is not very different from traditional computing, but with a lot of with some level of differentiated approach, because here you are dealing with data. This should be possible to do. Yes, it should be possible to do.
Thanks, Sundar. We are on the top of the hour, but there are a couple of more questions, both related to how do I get into AI world. So I'll combine the two questions. This would probably be the last question, Sundar. What is the first step to get into the world of AI? And also, the second question is, I'm pursuing the MBA in pharma management. I'm interested towards analytics and deep learning. How and from where should I begin? What skills should I gain to be suitable for the industry, and what courses should I go? So it's basically, how do I enter into the world of AI? Both these questions.
Sure. So, I mean, just look at the screen, whatever you are looking at. These are all great places to get started. The last one, Experience DLI online courses. DLI expands to Deep Learning Institute, hosted by NVIDIA. Many of the courses are free, and many of them are charged also. I mean, it starts as low as $30, and some of the advanced courses are $90. And this is just NVIDIA courses. There are I don't have to tell you the popular online learning platforms today. There are like many of them, and there are some of them which are really, really good, like Coursera, etc. So go and do a search and get started there. Have a feel of it. If you are totally not familiar with the field, at least understand the basics. Get a feel of what it is. And there are so much free online courses, good courses. Because they are free doesn't mean they are substandard. Extraordinarily good courses are available, and that's where I would request you to get started. And please do make use of all the 4 links that I have listed here. These are good links. And just going through these links and understanding the content there will get you a very, very good introduction into the exciting world of AI.
Thanks again, Sundar. I think with that, we will stop taking the questions for now. And then I think we have covered all the questions that have come in as well. So thanks everybody for the questions. Thank you, Sundar, for the wonderful session and a great Q&A session. Really appreciate you taking time on Sunday and sharing your knowledge with all of us. It was a pleasure having you today on the session. And thanks everybody for attending. Hope you enjoyed the session.
Thank you, Sarah. Thanks, Samir. Thanks, Devesh, and all my colleagues in PAI for giving me this opportunity to talk to these people. And thanks to all the attendees. It was a pleasure talking to you all. Have a good rest of the Sunday.
Thank you. Thanks.
Thanks, Sundar.
Thanks, Sundar.